Hello and welcome to yet another video of Cornerstones of Math. Today I am going to talk about prime numbers. Here I am going to prove one simple and basic property regarding prime numbers. So the problem says, for a natural number n greater than 1, prove that if all prime numbers less than or equal to square root of n do not divide n, then n is a prime number. For the proof, we use the famous proof by contradiction. So let us deny the conclusion and suppose that n is not a prime number. Then we can write n as L times m for some natural numbers L and m that are both greater than 1. Now I will introduce some divisors of L and m, some prime factors of L and m. So let p and q be the prime numbers such that p divides L and q divides m. And these prime numbers p and q definitely do exist. For example, even in the worst case, where L itself is a prime number, so that L cannot be divided by any natural numbers less than L, we still have p as L itself. So yes, they do exist. Then pq divides Lm, and since Lm equals n, this means pq divides n, so pq must be less than or equal to n. This is the range of the product PQ, and now we have to think about the individual range of P and Q. If P and Q are both greater than square root of n, then the product PQ is greater than square root of n times the square root of n, which is n, hence contradiction. Therefore, we have P is less than or equal to square root of n, or Q is less than or equal to square root of n. That is, at least one of them is less than or equal to square root of n. And since p and q are prime numbers, this means that there exists a prime number which is less than or equal to square root of n among the divisors of n. And this contradicts the given condition that all prime numbers less than or equal to square root of n do not divide n. Therefore, we have the conclusion n is a prime number, which concludes the proof. Now this looks like rather a simple proof, but the theorem we have just proved here is quite useful when you're trying to find out whether a certain number is a prime or not. Suppose that you're trying to determine whether some natural number n is prime or not by so-called brute force. That is, you divide n with every prime number less than n to find out any prime factor of n except n itself, if such thing exists. When doing so, obviously you don't have to check prime numbers that are greater than 2 over n, because the greatest possible divisor for any natural number n cannot exceed n over 2. But the theorem we have just proved set a much smaller number, square root of n, as an upper boundary. That is, we only need to check for prime numbers that are less than or equal to square root of n. For example, let us find out whether 211 is a prime or not. Now, since 211 is greater than 14 squared and less than 15 squared, the square root of 211 is greater than 14 and less than 15. Therefore, we only have to check for prime numbers less than or equal to 14, which are 2, 3, 5, 7, 11, and 13. And most of the process is not too complex. 211 is an odd number, so it is not divisible by 2, and the sum of digits is 2 plus 1 plus 1, which is 4, so it is not divisible by 3, and it does not end with 0 or 5, so it is not divisible by 5, and checking the divisibility for 7, 11, and 13 by doing the actual division does not take that long, so 211 is not divisible by 7, and it is also not divisible by 11, and it is also not divisible by 13. So 211 is not divisible by any of these prime numbers. Therefore, we can say that 211 is a prime. And that's all for today's video. If you enjoyed this video, please check this 100th video of mine where I find all prime numbers under 100 to find the least common multiple of all natural numbers from 1 to 100. Thank you all for watching, and I will see you in another video.